The first rule is known as the junction rule. A junction is any place where you have to make a decision about which direction to take. You might peel off to the left or to the right, or simply go straight ahead. A ski area with its chairlift and ski runs serve perfectly to illustrate the concept of the junction rule. Let's consider 100 people riding the chairlift to the top. Once at the top, every one of those people have to get off at the same spot. But once at the top, each person must decide which run they want to take to the bottom if they want to ride this chairlift again. So if 100 people enter the runs at the top and they all want to ride the lift again, then 100 people must exit the runs at the bottom to get back on the lift. That same thing can be seen in an electric circuit. If 100 charges enter a junction, then 100 charges must exit the bottom end of that junction. The junction rule is a statement of the conservation of electric charge. If 100 people enter the runs at the top and want to ride this lift, then 100 people must exit the runs at the bottom to get on that lift. Same thing with electric charge. If 100 charges enter a junction, then 100 charges have to exit the junction on the bottom end. Once again, the junction rule is a statement of the conservation of electric charge. All charge has to be accounted for. Recall that we've already solved for I3. We can go back and use this substitution, or you could go back to equation number 3. It's not on my boards because I erased it. But if you go back and look at equation number 3, you could solve that equation for I3 as well and make your substitutions. But since I've got this one on the board, I'm going to go with this route. So my next step will then be to take I2 into number 4. Okay? So that's going to be my next step. Well, I can see the equation right over here. I can see that it's positive E1 minus I2R1, etc., etc., etc. So I'm going to go straight to making my substitutions from there. So when I have I3, I will have 10 volts minus 470 ohms times I2, which is negative 0.0107 amps. Remember that you have to use the whole SI unit. The SI unit for current is in amps. Now, although it's more commonly communicated as milliamps, we still need to use the measurement of amps. So, negative 0.0107 amps, okay, minus 220 ohms times negative, okay, and time to erase this. Okay, you have that as well. Okay, so 220 times minus 0.0107 amps, okay, minus 5 volts. All right, and all of this is divided by R1, which is 470 ohms. Carrying out the arithmetic, checking our numbers first of all, positive 10 minus 470, negative 0.0107 minus 220 times a minus 0.0107 times minus 5 divided by 470 is equal to positive 0.0263 amps, which is commonly communicated as 26.3 milliamps. Positive. Okay? All right. Okay, well, there is this is I3, and this right here is I2. Now that we have I2 and I3, we can go back to equation number 1 and solve out for I1. And so what we do is we take I2, I3 into number 1. Okay, so recalling that number 1 was I2 plus I3, we now have negative 0.0107 amps plus 0.0263 amps, and solving for I1, you get a value of 0.0158 amps. amps. Okay, and that is positive. This is a positive number. Okay, well, we have all of our variables on the board here. Now check it out. Signs in physics show direction. We had a positive sign for I3 and a positive sign for I1. But we got a negative sign for I2. Now, this is the beauty of it. We arbitrarily chose the directions of 2 and 3 to be what they were. It's just, that's what I felt I wanted to do. Okay? You might feel different. You might make a different decision than I did. But here's the thing. Currents aren't negative in a real circuit. What happens is we simply chose the incorrect direction. So rather than going down that middle branch, what we had was it was actually going up that middle branch. Now I could have seen that had I looked at the positive terminal of the battery going up, and we even talked about it. But I wanted to go down so I could show you that the problem in the mathematics can solve your error for you. The magnitude won't change, just the direction. All right, well, what we can do with this information now is go back to our breadboard and see if we can experimentally determine these values. So let's do that. Let's go back and check out the measurements on our breadboard.